Scientists at the CERN Research Centre in Switzerland believe they may have discovered the Higgs boson particle, believed to be the missing link in our understanding of the formation of the universe. The breakthrough is the culmination of more than 40 years of research.
What if CERN's most powerful experiment didn't just study reality, but briefly disturbed it? Deep beneath the Swiss-French border, the Large Hadron Collider runs tests meant to uncover the universe's hidden rules. But according to someone once inside CERN, one experiment may have produced something no one expected. It lasted for less than a trillionth of a second, yet raised questions that remain unanswered. Was a boundary crossed during that moment? And why has what was reportedly observed never been fully explained? The door at CERN. It sounds like something straight out of science fiction, a massive machine capable of opening a fleeting door to another dimension. According to some insider reports, that is exactly what the Large Hadron Collider, or LHC, at CERN has been doing in its quest to study the deepest secrets of the universe. The notion is that during proton collisions at extremely high energies, a portal briefly appears, opening a window into subatomic or multidimensional realms. This door lasts only for a split second, about 10 to the negative 26 seconds, before closing again, returning us to what seems like normal reality. The idea is unsettling because it ventures beyond theoretical physics into the territory of unknown consequences. Despite the official stance that the LHC is simply smashing particles to understand the fundamental forces of nature, whispers from former staff and independent investigators suggest otherwise. Some say beings have been observed passing through these portals, hinting at contact with entities existing beyond our dimension or even from the future. This claim echoes conspiracy theories about time travelers and alternate timelines intersecting as a result of the Collider's experiments. While this sounds incredible, it underlines a growing unease about the true nature and scope of CERN's activities. If such a door exists, what exactly might come through it, or escape? This uncertainty is intensified by statements from scientists who once described the LHC as more than just a collider, but potentially a door itself. Sergio Bertolucci, a former CERN director, went as far as to say that through this door, something might enter our world, or we might send something out to other dimensions. He emphasized the brief and delicate nature of this event, framing it as a breakthrough in understanding nature. However, he also cautioned that, at the time, the door had no practical use. This raises philosophical and scientific questions. What untapped potentials linger at the edge of such experiments? The mystery deepens because this door, if real, operates at energy scales and conditions that are still barely understood. CERN's collisions now smash protons at record energies of 13.6 trillion electron volts, pushing beyond previous limits. These speeds approach the speed of light and create extreme conditions where space and time themselves might behave differently. The possibility of bridging physical realities, even temporarily, starts to feel less like fiction and more like a dangerous possibility. Yet this remains largely speculative, with official channels emphasizing safety and scientific rigor. The public has maintained rumors about portals and anomalies for many years because unusual natural events and mysterious occurrences have raised public concern about these unexplained phenomena. Time perception changes, and the Mandela effect, together with strange cosmic events which people say happen during LHC experiments, serve as evidence for their claims. The events that happened with CERN experiments create greater uncertainty about their experiments, which begin to reveal hidden knowledge. The concept behind a door needs to function as an entrance because it connects different dimensions which permit movement between two distinct realms of existence. The public knows about these theories through incomplete information which receives regular dismissal, but insider witnesses provide evidence for a narrative which exists beyond official reports. The disappearance of articles raising these concerns and the sudden silence of some researchers feeds speculation about secrecy and control. The door concept exists as a fascinating mystery which scientists have not yet solved, but it now presents itself as a scientific puzzle that will lead to an upcoming discovery which will be revealed during our following discussion. The door metaphor remains popular because it represents scientific progress toward unknown territories, despite the absence of solid evidence. The situation creates possibilities that defy our current understanding of both physics and the fundamental nature of time and existence. The door functions as both a physical entrance and a metaphorical boundary that defines the limits of human understanding towards the natural world. The existence of this entity, which exists only for a short period, causes intense worry and widespread interest according to its current state. The situation presents a scientific project that exists in a state between its major discoveries and its potential hazards. The Large Hadron Collider needs a demonstration that helps people comprehend its functions and its subatomic research findings at their most fundamental level. As the collider rips protons apart, it reveals previously hidden particles and fundamental building blocks of matter, pushing physics into uncharted territories. Particle collisions and new discoveries. At its core, the Large Hadron Collider is a remarkable feat of engineering. A 17-mile circular tunnel buried deep beneath the border of Switzerland and France. Inside, beams of protons travel in opposite directions at nearly the speed of light until they collide with immense energy. These collisions recreate conditions similar to those just moments after the Big Bang, giving scientists a glimpse into the universe's earliest state. Powerful detectors like ATLAS, CMS, ALICE, and LHCb then analyze the debris, searching for particles and forces that make up the fabric of reality. One of the LHC's most significant achievements was the discovery of the Higgs boson in 2012, often referred to as the God particle. This particle helps explain why matter has mass and why it forms the structures we see around us. Its discovery confirmed decades-old predictions and marked a breakthrough in particle physics. Since then, CERN's experiments have pushed energy levels even further, now reaching 13.6 trillion electron volts. In recent runs, researchers have also observed new exotic particles, offering deeper insight into how quarks interact. Experiments like the ALICE study quark-gluon plasma, while LHCb investigates the imbalance between matter and antimatter in the universe. The existing situation shows a severe lack of equilibrium. The Big Bang should have created equal amounts of matter and antimatter, which would then annihilate each other in an instant. The universe exists today because of a cosmic error that produced matter instead of nothingness. The scientists at CERN conduct experiments to investigate this mystery, which explains the observed phenomenon. The scientists at CERN achieved their first successful antimatter experiment in 2018, when they managed to contain antimatter while transferring it through 2 locations, according to their results, which matched the energy output of 20 Hiroshima nuclear bombs. The researchers have discovered new scientific possibilities through their work. CERN researches the fundamental question of how antimatter interacts with gravitational forces. Antimatter would prove to have different gravitational reactions because it behaves completely differently from all known physical phenomena of matter. Current experiments show that antimatter falls under gravity much like matter, but scientists continue to look for different results. The latest tests reduce testing mistakes because they improve our understanding of universal laws that govern the universe. The accomplishments of CERN demonstrate its dedication to fundamental research work as a foundation for exploring unproven possibilities of hidden phenomena that exist in higher dimensions. The discoveries establish a foundation that enables researchers to develop theories that propose our universe exists as one component within an extensive cosmic framework. The high-energy particle collisions enables scientists to investigate atomic structures while accessing previously unreachable levels of reality. The science establishes a solid foundation, yet it introduces essential inquiries that demand examination. The collisions have the potential to discover new particles and forces, which scientists think might lead to the discovery of portals that connect different dimensions. The question connects with ongoing research about the existence of extra dimensions, which scientists believe hold answers to fundamental universal secrets. Understanding these ideas requires us to look at why physicists are so interested in extra dimensions and what CERN hopes to find there. The search for extra dimensions. Physicists have long proposed that our universe may contain more dimensions than the four we directly experience, 3 of space and 1 of time. These extra dimensions could help explain some of the biggest mysteries in physics, such as why gravity is so much weaker than other fundamental forces, or why the universe's expansion continues to accelerate. The Large Hadron Collider is one of the few scientific instruments capable of testing these theories by recreating extreme conditions where hidden dimensions might influence particle behavior. This is not science fiction, but an active area of research in modern theoretical physics. Extra dimensions may be compactified or hidden from everyday perception, folded so tightly that they escape direct observation. Some models, including string theory and brane world scenarios, suggest that gravity might extend into these dimensions. This could explain its relative weakness compared to other forces. CERN's experiments are designed to search for signs supporting these models, such as unexpected particle interactions or the possible formation of microscopic black holes during high-energy collisions. As the LHC continues to operate at increasingly higher energy levels, it approaches thresholds predicted by alternative theories. Some scientists argue that if tiny quantum black holes were formed, they could only exist within the framework of extra dimensions. CERN has acknowledged this theoretical possibility, while emphasizing that such black holes would decay instantly and pose no threat. Detecting them, however, would be a major step toward confirming that our universe is more complex than previously believed. Certain theories also suggest that the energy levels required to produce these effects are now within reach of CERN's upgraded runs. Models like gravity's rainbow predict that phenomena tied to extra dimensions could occur above specific energy limits the collider is beginning to approach. This proximity fuels both excitement and caution within the scientific community. Beyond black holes, the concept of an interdimensional connection has also been discussed in relation to these models. Under extreme conditions, hidden dimensions might briefly interact with our own. While mainstream science remains careful about such interpretations, the relationship between theory and experiment keeps the possibility open. Exploring extra dimensions raises deeper questions about time, reality, and the structure of existence itself. If such dimensions exist, they may hold answers to puzzling observations reported around high-energy experiments. Each discovery moves us closer to understanding what might lie beyond the limits of known physics and how our universe fits into a larger framework. The possibility of black holes and quantum risks connected to these phenomena challenges both scientists and society in ways that are hard to ignore. Black holes and quantum risks. The idea that the Large Hadron Collider could create black holes has fueled anxiety and speculation for years. In theory, if two particles collide with enough energy, above a certain threshold, it's possible they could form microscopic or quantum black holes. These would be unimaginably small and short-lived, decaying almost instantly into ordinary particles. CERN has stated that while the creation of such black holes is highly unlikely, it remains possible under certain theoretical models connected to extra dimensions. Mainstream physics emphasizes that even if these quantum black holes were formed, they would pose no danger. Their lifespan would be so brief that they wouldn't have time to grow or consume surrounding matter. Most physicists agree that creating a stable black hole with a particle collider is beyond our current capabilities and contradicts established theories. Still, the acknowledgement of even a minute possibility has sparked public concern and ongoing debate, where theoretical science meets real-world fears. One reason microscopic black holes are often linked to extra dimensions is that some models suggest gravity could become significantly stronger at subatomic scales within those dimensions. This might lower the energy needed for black hole formation, making the LHC's current output relevant. The collider now operates at 13.6 trillion electron volts, levels approaching thresholds predicted by speculative models like gravity's rainbow. This raises questions about whether we're reaching energetic frontiers once thought to be out of reach. Safety stands as the primary concern despite all available options. CERN explains that Earth experiences cosmic rays, which possess much greater energy than that which creates dangerous black holes. Natural processes would create microscopic black holes, which become safe because their fast decay leads to instant disappearance. CERN supports its claim that LHC experiments pose no world danger through this line of reasoning. The situation eliminates some worries but still maintains another level of anxiety. Researchers need to study how energy from these quantum events gets distributed. The energy from microscopic black holes will vanish when they reach their end. The study investigates whether local ecosystems and electromagnetic systems experience any hidden or obvious environmental disturbances. CERN produces magnetic fields that reach strength levels that exceed Earth's natural magnetic field by several 100,000 times, showing scientists want to study the accumulated effects that happen throughout time. The public grows more worried about the collider because its operations demand both extensive resources and complicated procedures. The LHC operates almost continuously through international treaties, which reduce legal oversight, creating both scientific advancements and unknown future possibilities. Lawsuits and petitions about unknown risks emerged before the 2008 startup of the system. The legal framework of CERN operated outside direct national control, which restricted the power of regulators to enforce regulations. Scientists agree that present scientific theories cannot predict any disastrous outcomes despite the ongoing discussions. The current dialogue shows two competing objectives that scientists attempt to study while they control the unknown elements that stem from their investigations into fundamental scientific questions. Transitions like a fragile thread weave these hard science debates into accounts that suggest something more enigmatic is unfolding behind the scenes. Insiders and unexplained phenomena. Behind CERN's massive machines and complex scientific language, insider accounts have stirred both curiosity and unease. Some former researchers and whistleblowers have described unusual phenomena that seem difficult to explain. Reports of figures appearing near experimental zones, timelines seemingly intersecting, and even alleged interactions with entities said to originate from the future. One former government scientist, Dan Burrish, has claimed that these beings may come from roughly 45,000 years ahead on a separate timeline. If true, this would suggest a possible breach not only in space, but in time itself. These insider stories echo a growing public feeling that reality may not be as stable as it seems. This sentiment often shows up in discussions about the Mandela effect, where groups of people remember historical facts or cultural details differently from official records. Some point to changes in familiar media, like film intros or well-known character designs, as subtle signs of shifting timelines. While controversial, these ideas have fueled speculation about whether advanced experiments might be influencing more than just subatomic particles. Adding to the mystery are unusual events that have coincided with CERN milestones. In 2016, during the opening of a major tunnel in Switzerland, a widely discussed ceremony took place. Around the same period, a strange spiral formation appeared in the skies over Norway, along with reported fluctuations in Earth's magnetosphere. Although no scientific link has been confirmed, the timing has prompted debate about possible hidden effects tied to high-energy experiments. Some of the most unsettling stories involve individuals connected to CERN's research. One account describes a physicist named Dr. Edward Mantle, who was reportedly found dead after investigating patterns in neutrino flows between Earth's magnetic poles. His notes allegedly compared the universe to pages of a vast book, with each page representing a separate dimension. However, no reliable record of Mantle's existence has been found, deepening speculation around missing knowledge and suppressed discoveries. Symbolic elements at CERN have also drawn attention. The Shiva statue on site, representing cosmic destruction and creation, along with interpretations of CERN's logo, have added layers to public curiosity. While officially explained as cultural or technical representations, they continue to invite alternative interpretations. Despite denying any supernatural or interdimensional activity, CERN has addressed these rumors publicly. Yet, the need for clarification reflects growing fascination and concern about what might truly lie behind their experiments. Unraveling this tangled web of science, secrecy, and speculation demands we look closely at the frameworks of authority and governance surrounding such a powerful project. Legal oversight and global impact. The Large Hadron Collider at CERN operates under a unique international framework that places it beyond the direct control of any single nation. Established by treaty in 1954, CERN is managed collectively by more than 20 member states. This means national courts cannot directly intervene, and oversight depends on complex multinational agreements. While this structure enables global cooperation, it also raises questions about accountability and transparency. The lawsuits that occurred before the collider started operating in 2008 stemmed from two main concerns scientists raised about potential dangers, which included both microscopic black holes and unexpected results from their experiments. The court dismissed these cases because CERN operates under a legal framework that prevents individual governments from controlling its activities. The absence of a designated authority results in divided supervision, which becomes difficult to determine. CERN uses its governance system to control how information reaches the public. The presence of multiple member states leads to cautious messaging, which requires close management. The Collider project continues to create new safety concerns because of its extensive and intricate design, which raises fundamental inquiries about who should take responsibility and how countries should work together. CERN requires effective supervisory systems that maintain responsibility during its upcoming upgrades and 2029 restarts. The process of discovering new knowledge needs to proceed while the world impact of research needs to be studied. CERN's Large Hadron Collider operates where known science meets the unknown, probing not just the smallest particles, but the deeper structure of reality itself. As the collider continues to push the limits of what we can observe, our curiosity grows right alongside our questions. If this deep dive sparked your imagination, don't forget to like, share, subscribe, and watch the next video now appearing on your screen to keep exploring what lies beyond.